In this video, we briefly explore the relationship between the first derivative of a function and the graph of the function. So we're going to cover how the first derivative relates to either increasing or decreasing behavior in the function. Then we'll work 3 examples of finding the intervals on which a function is increasing or decreasing based on the graph of the function, based on the graph of its derivative, or based on a formula given for the function. So to start things out, we want to establish that the sign of the first derivative determines whether the function is increasing or decreasing. And we're just staying grounded in our informal geometric intuition here rather than providing a formal proof of this relationship. So at the top of the screen, we have a reminder of what it means for a function to be increasing or decreasing. When we say increasing, we mean the function goes up as we move from left to right. So in our definition, we're saying that f of x is increasing on some interval I if for any two x values, x1 and x2 belonging to I, x1 being less than x2, in other words, 2 is left, implies that f of x1 is less than f of x2. In other words, if x1 is to the left of x2, then f of x1 is below f of x2. It's lower on the graph. And we can see this down in our picture of our increasing function. There's an x1 less than x2 down there on the x-axis. And we see that f of x1 is a lesser value than f of x2, putting it below f of x2 on the graph. And this is just a very precise way of saying what we mean by an increasing function. It's going up as we go to the right. Now the definition is similar for a decreasing function. We say f of x is decreasing on some interval I if for any x1 and x2 belonging to I, x1 being less than x2 implies f of x1 is bigger than f of x2. And we see the picture of that on the lower right. I have, again, an x1 to the left of x2, so that's a lesser x value. And this time, f of x1 is a bigger y value than f of x2, so my function goes down as I go to the right. So what does this have to do with the derivative? Well, if we place a tangent line on the graph of this increasing function, that's always going to have a positive slope. In other words, saying a function is increasing is equivalent to saying that the first derivative is positive. And of course, we can do a similar thing to the decreasing function. Anywhere we place a tangent line on that decreasing function, that tangent line is going to have a negative slope, meaning the first derivative is negative. So that's really it for the theory in this video. Positive derivatives correspond to regions where a function is increasing, and negative derivatives correspond to a region where the function is decreasing. And now we're ready to work 3 common types of problems. So in our first example, we're told we're looking at a graph of a function f of x on the interval -5 to 5, and we want to use the graph to find all the intervals on which f of x is increasing and decreasing. Now, it's a fairly safe assumption in a problem like this that the boundaries of the regions of increasing and decreasing are going to happen at integer values, just to make it so we can actually read the answers off of the graph. So remember, increasing just means going up as you go to the right. So we start out increasing all the way from -5 to, it looks like 1. That's when the function shifts to decreasing, in other words, going down as we go to the right. But then it shifts back up to increasing again toward the end of this interval. So it's going to shift back to increasing from 4 to 5. So we're going to say it's increasing on -5 to 1 together with, so we use a union symbol for that, together with the interval 4 to 5. Now the function is decreasing, in other words, going down as we go to the right, on the interval 1 to 4. So textbooks are probably going to vary on whether or not they state these as closed intervals or open intervals. But if you look at our original definition for increasing and decreasing, those definitions are satisfied on these closed intervals. If I take any two x values where x1 is less than x2, we're going to satisfy the definition for increasing on these closed intervals and the definition for decreasing on this closed interval. Now that's not really a big deal, but I think the textbooks do sort of vary in style concerning whether or not these are open or closed. Okay, so that problem was pretty straightforward. In the next example, we get a little more abstract. We're given a graph of f prime of x. So we're actually looking at a graph of the derivative of the function that we're concerned with. And this is shown on the interval -3 to 5. And again, we're asked, where is f increasing and decreasing? So we're not talking about the function we're looking at. We're talking about the function we differentiated to get this graph. But we know that when the derivative is positive, the original function is increasing. And when the derivative is negative, the original function is decreasing. So all we have to do is look for where this graph is positive and negative, not where this graph is increasing or decreasing. So the original function f is increasing when the derivative graph is positive, in other words, above the x-axis. So it looks like that's happening on the interval -2 to 2. So these are my transition points at the zeros of f prime. And from -2 to 2, this graph is above the x-axis. In other words, those are positive values of f prime. So I'm increasing on -2 to 2 together with everything to the right of 4. So the interval of 4 to 5. And again, the original function is decreasing if the derivative is negative. So on the graph of the derivative, that's just all the intervals where it's below the x-axis. This happens on -3 to -2 and 2 to 4. And we're done with that one. Finally, we have an example where we're given the formula for a function, and we're asked to find out where this function is increasing and decreasing. So what we want to do is study the derivative of this function and figure out where that's positive and negative. So we start by taking the derivative, and f prime of x is going to be 3x squared minus 3. And to find out where this thing is positive and negative, it's really useful to find out where it's equal to 0. So 3x squared minus 3 is equal to 0. I can divide a 3 out of this thing, and I find that x squared minus 1 is equal to 0. And there's two ways to approach this. I could factor it, or I could just move the 1 over to the other side and take the square root. But you do need to be careful to get both solutions. So I think the factoring method makes that most clear. This is a difference of two squares. It factors into x plus 1 times x minus 1. So I get the equation x plus 1 times x minus 1 is equal to 0. Now that equation is true if either one of those factors is equal to 0, which means I get two solutions, x equals 1 or x equals -1. So these are the spots where the derivative is equal to 0. And that means these are the spots that are separating regions where the derivative is positive or negative. So it's really useful here to bring in a number line to visualize what's going on. So this is a number line where we're looking at the values of f prime, the first derivative. And I'm really interested in these two spots, -1 and 1, because my first derivative is equal to 0 at these two spots. Now, if I look to the left of -1, I'm trying to figure out what's the sign of f prime. Is it positive or negative? And maybe it's helpful to just highlight the factored form of this original function, f prime. Factoring a 3 out of it, I have a 3 times x plus 1 times x minus 1. Now looking at that, I can tell if I take an x value to the left of -1, that's going to make the first factor negative because I have a negative number bigger than 1. The second factor is also negative because I'm just subtracting 1 from x, and a negative times a negative is a positive. So my first derivative is positive to the left of -1. In between -1 and 1, that means x is to the right of -1, which means my first factor in this factorization is going to be a positive number. The second number in my factorization is still negative. So a positive times a negative is a negative. Now I do want to point out that it's really common to teach students to just sub in a specific test point. That is an alternative way to approach the problem. So you could just take a test point on this interval -1 to 1 and sub it into this formula and see whether or not f prime is positive or negative. So the most common choice of test point there would be 0. If I sub in x equals 0, I get 3 times 1 times -1, which is negative, and it agrees with my first method. Now to the right of 1, if I look at my first factor in f prime, clearly positive. Second factor, positive, because if I subtract 1 from something to the right of 1, I still get a positive result. So I have a positive times a positive, which is a positive. So remember, when the derivative is positive, I'm talking about a region where the function is increasing. When it's negative, that's a region where it's decreasing. So we get our answer, f is increasing on -infinity to -1, and also on 1 to infinity. And the derivative is negative, so f is decreasing on the interval -1 to 1. Finally, let's take a look at the graph of our original function f of x to see if we agree with this assessment. I can see that it has a positive slope. In other words, it's increasing. It's going up as I go left to right, all the way from as far left as I can go. So this is going to go all the way off to -infinity to this point, which happens at x equals -1. So increasing on -infinity to -1, also increasing from here, which happens at x equals +1, all the way off to the right. So that agrees with our answer for where this thing is increasing. And then in between -1 and 1, I can see my function is decreasing. It's going down as I go to the right. So you may have noticed there's a connection between increasing and decreasing analysis and the location of local maxima and minima for a function. Right there, I've got a local maximum because my function switched from increasing to decreasing. And right there, I've got a local minimum because my function switched from decreasing to increasing. In the next video, we get into a detailed analysis of how we locate local maxima and minima by studying the first derivative. I'll post a link to that video at the upper left, and I'll see you there.